Hello, welcome everyone. Thank you to Jose and all the other organizers for setting this up. I was just telling him that if this works out, then I'm never going to get on an airplane again because I can now give talks internationally from my office. So I want to talk to you today about discrete Morse theory. This is a sequence of results from a few years ago. And as a mathematician, your temptation is to just talk about the last one or two things you've done. And this is work from about 3 years ago, but I'm really excited about it because it just got published. So you're going to hear an old story, but hopefully it's a nice story. So let's start very, very simply. I want to start with applied topology and basically topological data analysis, if you know what that is. It starts with measurements. You make a measurement, and this is sort of a scientific process where you get a data set because someone goes out and collects some information, and then you impose a metric structure on it. So you have a sequence of metric spaces getting bigger and bigger. And then you do a little bit of algebra, put it on a computer. And the hope is that at the end of this process, you learn something, you get some insight. And the sort of typical technique in this field is persistent homology. It starts like this. Say you have this collection of data points that you see on the screen, and you just there's a shape that's underlying these data points, and to detect that shape, you just thicken the points a little bit, the way you see right now. And now you see sort of a circle. And this information, what happens, what comes and goes, what changes in this shape as you're thickening your metric space, can be recorded in a sort of combinatorial way, and it's called a barcode, and you can read all about it. So the 0th barcode just keeps track of connected components. And you see in the beginning, all the points were their own little piece. And as you thickened, pieces started merging. So you record the radii at which they started merging. And one of them, this one connected component, sort of lasts for a very, very long time. And similarly, the first barcode records the one-dimensional homology, or sort of the loops. So you see there's at some radius a loop formed, and that's the long line in the first barcode. Anyway, that's the preamble, and here's the outline of the talk. This talk is arranged like a cappuccino. This is honest to goodness how this talk is going to go. At the beginning, we will talk a little bit about the real honest applications of algebraic topology. Then we'll filter through, that's sort of the foam on top of the cappuccino. Then we'll filter through to the sort of computation, which is the milk, and then we'll get to the coffee, which is the theory. So we're going to go sort of down this cappuccino from the foam all the way down, and Jose correctly is taking a sip of his drink. That's the right thing to do. All right, so let's see. There are too many applications now to give you a full summary. Here are 3 that I know. So persistent homology has recently been used to, by recently now, it's 10 years ago, this work, to detect when a bunch of sensors running around in a domain will actually cover it and detect all the invaders. It has also been used to describe the structure of granular media. So if you have a whole bunch of grain sitting in a silo and it experiences a little bit of pressure, how does that impact the size of the region where they're contained? And sort of my favorite application is application to protein compressibility, where you can predict how squishy a protein molecule is just from looking at its atom structure, like knowledge of where the atoms are embedded. And I will not have time to get into any of these in detail because it's not what I want to talk about, but you should know that the process of applying persistent homology or topological data analysis to any of these problems requires building what's called a simplicial complex, where you put in a d-dimensional simplex wherever d+1 sets intersect. And what I do is compute homology of such complexes. And the problem is essentially linear algebra. If you've ever computed homology in your life or thought about it, it just reduces to diagonalizing in a giant matrix. Like when data set gets very large, you can imagine there's billions of grains in the middle one there, and lots of atoms in a protein molecule. It's very, very expensive to do even this sort of baby linear algebra. And it's a serious problem. And I want to describe for a second why it's serious. So take a collection of data points. Say there's n of them. And now you want to compute homology as things get bigger and bigger. And so when things get bigger, you start intersecting edges. So if you had n points, in the worst case, you'll have n choose 2 edges. And then you have more. So n choose 3 triangles and so on. It keeps going. And it becomes this exponential mess. So the way we solve this problem, you want to compute homology even though the number of cells are very large, is you start throwing away cells that are not contributing to the homology. And this technique goes back to the work of Whitehead in the 50s. And it's sort of a beautiful story that has 2 parts. The first part is algebraic, and the second part is geometric. And I want to show you sort of both side by side because it's sort of the beginnings of K-theory, and there's tons of theory out here, but we're going to talk about a very computational thing. So say, imagine you have this matrix, and you should think about this as a boundary matrix of a simplicial complex. So what that means is on the columns, you have some d plus 1 dimensional cells. Along the rows, you have d dimensional cells, and the goal is to diagonalize it. Now, if you ever see a 1, a row with just one in it and zeros everywhere else, it's very easy to use that 1 to clear out the column up and down. Right? You just add whatever it is you need to add and clear out the column, and you don't have to make any extra effort. So what that 1 means is that there is a simplex that's connected that has only one higher simplex on top of it and no other connections. So geometrically, that looks like the gray stuff in this image, which means you have an edge with only one two-dimensional cell on top and nothing on the other side. Whenever you picture, this is completely equivalent. This matrix and that cell complex, I mean, you can go back and forth. You can get rid of that entire column, which means you can disconnect the big cell from everything else. And sort of zeroing out that column is exactly the same as pulling out these 2 cells, this edge and the gray two-dimensional simplex next to it. That doesn't change the homology that you want to compute. It doesn't change the number of holes, the number of connected components, but it reduces this giant matrix to a simpler one, or that picture to a much simpler one. Is this okay? Are there any questions so far?
Not yet.
No. Good. All right. Let's go on. So you take this this story which sort of takes a big cell complex and removes 2 cells at a time from it, and you want to remove more than 2. So you want to build a sort of a way to crank this machine sort of automatically, where you just take away more and more cells. By the way, you'll notice if I take away these 2 gray cells, then I find 2 more cells, edge and 2 simplex pairs in the boundary, where I can push in even more. You can just iterate this scheme, and so you get a new version of Morse theory. Smooth Morse theory, then this is what you think of it as a new Morse theory. It was introduced. There are many versions of it going back to the 70s, but the one I'm going to talk about was the mid-90s by Robin Foreman. So again, you're going to take a nice cell complex. I've written CW here, but it could be a simplicial complex, a complex built of cubes, any sort of cell decomposition of a space. And you start operating on pairs of simplices or cells that are sort of one apart in the dimension. So here's the simplest sort of example, right? So look, you found a free pair. You have that edge with only 1, 2 simplex on top and nothing on the other side. So you can just have gotten rid of them. And now you see there's a vertex and an edge pair that have the same property. There's nothing else on top of that vertex except that edge. So again, you get rid of them. And now you're stuck. Every vertex has at least 2 edges on top. So you cannot just take an arrow and remove things. So you do something strange. You take a top dimensional cell and just mark it as removed, even though now you're changing the topology. If that cell is missing, then you lost a one-dimensional operator. The circle becomes a sort of, that has a space that has the homology of a point. So anyway, you remove it, and then you find more collapses of this form that you can make. Those are gone, 2 at a time, again, 2 at a time, and now this vertex that is left, again, you sort of mark it. Now, what I've just described for you is a sort of Morse theory. You should think of it as a function which assigns values to all the cells, and the times where you had to change the topology by marking a cell especially, and you couldn't get rid of it in a pair, those are the critical values, the critical points of that function. So here's the full complex and the sort of baby complex on the side. So on one side, on the right of your screen, you have the entire structure. There's a cell complex, and then there are these arrows that tell you how to push in. And on the left side of the screen, there's what it reduces to. There is a single chain in dimension 1, a single chain in dimension 0, and you can build a chain complex with just these chain groups. And that chain complex with the fewer chain groups has the same homology as the one on the right, the big one. So if you wanted to compute the homology of the chain complex on the left, it's a 1-by-1 matrix. And if you want to do it on the right, it's a 6-by-5 matrix. And so already, even in this small example, you've saved a lot of effort. So let's write down a little bit more precisely what is going on. There's a gradient vector field that allows you to flow from a cell to everything in its boundary, but whenever you have an arrow, you're also allowed to go up. Instead of going down to the boundary, you're allowed to go up to the bigger cell that you point to. So, and what you really want is, if you look at a zigzag, where you start down, up, down, up, down, up, where every time you go up, you must be flowing up along one of these arrows, you never want to make a loop. So this is called an acyclic partial matching on the cells, and this is playing the role of a Morse function. These zigzags are deciding the flow. So if you look at the picture on your left, you look at the edge that's highlighted. Now that's the starting point of the zigzag. Now you flow down to one of the 2 vertices in its boundary, up the arrow, and then down to the critical cell. So there's a zigzag of length 1 if you go on the right, and a zigzag of length 2 if you go on the left. And there are 2 zigzags connecting this edge to this vertex. And each of those can be assigned a number. And we'll talk about that in a second. But now let me tell you how you get the homology that you want from this reduced compressed representation. And you can sort of get as exotic as you like. So I have said, let F be a constructible cosheaf, and you don't have to know what a constructible cosheaf is. It's just a coefficient system. So on top of every cell, there's a vector space or an R module, and for every phase relation, there's a linear map or just a matrix. And in the simplest case, when you just want to compute homology, all the vector spaces have dimension 1, and all the maps are just the identity. So if F is confusing to you, just assume that everything in sight is rank 1 and has the identity map. So you have this cells with sort of algebraic data on top of them, and say you want to compute the homology with these coefficients. Now, take a pairing so that the overlaid map on top of any cell pair, x bigger than y, is an isomorphism. So if you just had what's called, if you just wanted to compute homology, you could take any acyclic pairing because the maps are all the identity and the identity is always invertible. Okay, now there's a new chain complex where all the chain groups are generated by things that are not the source or target of any arrow, the special cells that you had to keep out separately that did not collapse away. And between any two such cells, you look at all the zigzags which you got by chasing the arrows. So down, up, down, up, down, up. And that gives you a gradient path. If you're familiar with smooth Morse theory, this is just like the flow line against the gradient flow of a smooth function. And each of these gets a number that you can assign to it by just hitting it with f. So if in the nice case where you just want to compute homology, everything is the identity. So you get 1, minus 1, 1, minus 1, 1, minus 1. So those inverses. And that product is assigned to every path. And then you take a sum over all paths from the source to the target. And that's sort of the component of the boundary operator from C to C prime. And this new small complex that only has critical cells has the same homology as the old one, the big one. And you have much less computation to do because you got rid of most of the cells. That's what we know about homology. And this is actually the consequence of a deeper theorem that's about homotopy type. Unfortunately, we don't know much about it. So here's what we can say. The original cell complex is homotopy equivalent to another one, which only has the critical cells, but they're attached in some sort of strange way. And it's not clear if you read these papers how the critical cells are attached. You can recover the degrees of the attaching map, so you can compute homology, but that's about it. You cannot, you don't know whether something wraps around, some strange way. For example, if you had a torus, it's two loops, let's call them A and B, and then a disk attached, via A, B, A inverse, B inverse, if you've ever seen this presentation of the torus. The degree of the attaching map is always 0 because you had A and you had A inverse, you had B and you had B inverse. So you would never get the homotopy type of the torus. You just know that this has 1 point, 2 edges, and one two-dimensional generator. Okay, so this talk I want to correct this defect where we don't know the homotopy type. I want to build, using this discrete Morse theory, which is very useful for computing homology, a model for the homotopy type of the original cell complex. And the inspiration for this is some completely different work that happened at the same time as Foreman's that works for smooth Morse theory. So if you've ever seen smooth Morse theory, you start with a compact Riemannian manifold. You take a Morse function, which in this case is just the height function, and it has two critical points, which is where the gradient is 0. It's the south pole and the north pole. So the whole sphere is living between the maximum and the minimum. And from this data, you construct what's called a equation by Ralph Cohen, John Jones, and Graham Siegel back in 1995, and it looks something like this. So there's a category, and you don't have to know much about what a category is, but it has objects which look like that. So those are all the critical points. So in this case, like I said, there's one for the max and one for the min, and then there's a moduli space of gradient trajectory. So gradient trajectory is just, you chase the gradient of the function at the top and you just follow in the direction of steepest descent, just like any sort of, so for each point on the equator of this two-sphere, you get one flow line that's cutting normally across, like straight from the North Pole to the South Pole. So this equator is parametrizing all the flow lines from the top to the bottom. And then you build these are the morphisms in your flow category. So for each point on that circle, you get a line, a flow line from the top to the bottom. And so you just build the 2-point suspension of the circle. And that, you will notice, has the same homotopy type as the sphere we started with. So I would like to take this construction of the flow category and using this not in a very literal way, but just as inspiration, do this for the cell complexes in our discrete Morse theory. And this will give us a sort of something that has the same homotopy type. So the one thing, I mean, there might be many things here confusing to you depending on your background. I don't know what it is, but I think the scariest thing here is the classifying space. So if you know what a classifying space is, this theorem makes sense to you. If you don't know what a classifying space is, just think about you have a category, it has objects, every object is a vertex, it has morphisms, every morphism is an edge, and then you build a simplex whenever you have a string of composable morphisms. The simplest example is when your category is a poset. So there's a unique morphism from anything to anything else, and in that case, you build what's called the order complex of the poset. So an n simplex is just a chain of n+1 descending elements in the poset. So that's sort of a proxy for the homotopy type of a category or a poset. So, like I said, what I want is a discrete version of that story, a cellular version, a piecewise linear version, if you like, of this Cohen-Jones-Siegel construction for smooth manifolds. And now, two things go horribly wrong when you try to do this. And let me tell you what the obstacles are before I tell you how we can solve them. The first problem you get is over-attachment. So let's say you wanted to do this pairing that is indicated by the arrow. Now, on the level of homology, there's no problem. Nothing goes wrong. It's okay. You can just remove those two cells and you look at the zigzag paths from the remaining triangle to the other things and everything is fine. If you want to do homotopy, you have to figure out, just imagine pulling along the arrow. You have to figure out how to attach this triangle to that 7 shape that's at the other side of it. And right now you have a nice sort of combinatorial, simplicial complex. Now imagine that these two highlighted vertices, if you can see them, are the same, are identified. Now, the way you have to attach this triangle to the vertex on the bottom left, there are two different ways that it's attached. There's one ordinary attachment from before, and then there's the go around and attach it from the other side because of the arrow pushing you. So this is sort of a huge problem in terms of deciding. You cannot just look at what is a face of what. You have to sort of figure out the homotopy classes of paths from a cell to a lower cell. And this is not something that ever comes up in homology, but it does come up when you're trying to determine the homotopy. So there's a summary of this problem. I think I'll leave it there. It causes us some trouble, let's just say that. Okay, there's a second problem, which is sort of more immediate than even this over-attachment problem. And this is a problem of translating between smooth and discrete. And this happens all the time. So here you have, let's say, the height function on a torus, which is the first example of Morse theory anyone ever shows you. And let's say you take a non-critical point, a generic point, and I say, what is the flow line through that point? Where does it go? Which critical cell does it fall to? And of course, there's a unique, it just falls straight to the minimum. That's the sort of steepest descent line. There's a unique flow line through any non-critical point that goes to a critical point. And this is used in a very crucial way in the Cohen-Jones-Siegel paper because they want to send this manifold to the Morse category. And the way to do it is you take any point and you know which critical cell it goes to. So you can send every object here to an object there. Now imagine what happens in this very simple thing where you have flow that comes in and then discretely it's allowed to go in two different ways. So you have this non-critical cell, which is at the top. You see you have 3 squares and you take the edge on top of the middle square. The flow comes in, splits in 2 directions. So there's no unique flow line through it. There are a million flow lines through it. So there's no uniqueness of flow trajectories. And this happens all the time when you discretize. So on one side you have uniqueness, and on the other side you have an explosion of possibilities. So these two problems are what we have to solve. And let's go and see where the obstacles are right now. So here's a comparison between the smooth case, which is solved in 1995, and the discrete case, which we're still trying to solve right now. So the smooth case, you have a compact Riemannian manifold. In our case, we just have a regular cell complex, like a simplicial complex or a cubical complex or something. On the left side, you have a Morse function. On the right side, you have this acyclic pairing of cells coming from iterating Whitehead's construction. On the left side, you have critical points that have indices coming from the Hessian and the negative eigenvalues. On the right side, you have k-dimensional cells that are not the source or target of any of these Whitehead arrows. On the left side, you have gradient flow lines, and here you have zigzag paths of cells, even if they're not unique. And now, you remember how we went to this equatorial circle in the case of the smooth sphere? We have nothing. What is the analog of that? If you have a whole bunch of zigzags connecting one critical cell to another critical cell, up, down, up, down, up, down, up, down, how do I put a topology on that space of all zigzags? And that's the fundamental obstruction right now. So here's an observation. So the simplest way to put a topology on a finite set is to give it a partial order. That's, then you have the Alexandrov topology on it. And if you don't know what that means, that's okay. But really what I want to say is if you look at there's a 2-1-2-1 zigzag path in the bottom story going from left to right, and there's a 0-1-0-1 zigzag path above it. And I somehow want to say that the path above is less than the path below. And this is sort of intuitive right now. You don't have to know what anything precisely, but that's sort of the structure you want to put on these Whitehead paired sequences of cells. Is this okay? All right.
It's fine.
All right, going on then. So before we get into the details, we now need the classifying space of a category where you have posets of morphisms between any pair of objects. So the first question is, what is the classifying space? How do you build a topology on a partially ordered set? So here it is. So this is sort of the only difficult thing about this talk, really, and it is how to build a simplicial structure on a category which has, again, in our case, the critical cells are objects, zigzag paths are flow lines, and let's say we had some partial order between them. So between any two objects, there's a poset, partially ordered set of paths connecting from here to here via zigzags. So how do you build a space whose homotopy type you can actually measure? And again, the objects are vertices, good. Morphisms are edges. So now you're building a simplicial structure. And this is how you put in a two-simplex. So there's a zigzag path from X to Z. There's a zigzag path from X to Y and Y to Z. And if you compose these zigzags, then this one should be less than that one. And then you build a two-simplex. So here's a formal definition. You throw in a k-simplex if you have k+1 objects with morphisms going up the indexing so that any composite is less than what you would get via the direct path. So this is sort of a combinatorial simplicial set structure where you have an explicit decomposition of this category into simplices. And if you have functors from one category to the other that respect the partial order structure between these zigzags, then you get simplicial maps. And if you had natural transformations, you would get homotopy equivalences. Good. So this is all the stuff we need. We're now going to set up a theorem. And if you have a functor from objects, from one of these poset enriched categories to another one, then you can build what's called the fiber. So you should think of this as F inverse. There's a standard suite of theorems in algebraic topology that says if you have a nice map from X to y, and f inverse of every y is contractible, then your map is a homotopy equivalent. So we're now going to build the categorical version of this, right? So the picture you should have in your heart is you have an annulus and it's collapsing to a circle in the middle. And the fiber over every point in the circle is just a straight line that maps to the annulus. And so that's a homotopy equivalence because the fiber over every point is contractible. Good. So here's what the fiber over an object D looks like. So it's the image of some object in C, and if you have two of them, then this is how you put a partial order relation on them. So this diagram that I've drawn is a diagram in D, the category D, and on top of any object of D, you have a whole bunch of things mapping in from the image of the category C, and this is how you relate two of them. The double arrow just means less than in the poset structure among morphisms in D. So that middle arrow is just a partial ordering. Okay, you might have seen this category already. It has a ton of names. It's called the over category, a comma category, a slice category, an arrow category, because people keep needing it. And here's the theorem that we're going to use. It's my one hammer, the only hammer in this talk. And it's exactly the equivalent of the contractible fiber theorem in PL topology and everywhere else. So if the fiber over every object is contractible, remember, you know it's a category, so you can build a classifying space for it, so you know what it means for the fiber to be contractible. For every object, then this map of categories induces a homotopy equivalence between their classifying spaces, these simplicial sets that we built on them. So the goal now for us is to build appropriate categories where one is the simplicial complex before you did any of these Whitehead reductions, one is a Morse complex after the Whitehead reductions, and relate them somehow with contractible fiber so that you have a homotopy equivalence. Okay. So in order to do this correctly, it's not enough to just know the ordering relations between cells in a cell complex. You have to just go a little bit deeper than this is a face of that relation. And this is a beautiful construction of Robert McPherson that I don't think ever got published in this form until very recently. So here's a definition. So you have a cell complex X, and you build what's called the entrance path category. And I will describe it sort of carefully. Its objects are every cell of your cell complex is an object. And a morphism from one cell to another cell exists if that cell is a face of the first one, and every morphism is this sort of strictly descending sequence. And again, we're working over, the morphism should form a poset, and if every subsequence is less than this sequence. So there's a refinement. So this is a whole bunch of, there's a lot of definition stuff. Here's a picture. In this picture, X is a two-dimensional cell. Z1 and Z2 are it's one-dimensional faces, and Y is a vertex. So the category just for this piece has four objects: X, Z1, Z2, and Y. And there's a partially ordered set of paths from X to Y, these one morphisms, which look like this. So Y is the face of X, so that's one such descending sequence, X bigger than Y. That's the one in the middle. Then on the left, you see that X contains Z1 as a face, Z1 contains Y as a face, so that's a sort of bigger path. So the small path is less than the bigger path. And similarly on the other side, if you're familiar with barycentric subdivision, this should not be a strange construction for you. We're just chopping this up into smaller pieces. And you notice that sort of the minimal path, X bigger than Y, cannot decompose into anything else. When you compose two paths, they always get sort of bigger and bigger. So I just want to especially highlight these paths that are minimal, that just contain two things, X bigger than Y. and call them atomic because they don't split into anything further, and like use a circle just to remind ourselves when we have an atomic path. Okay, so what does this have to do with this cellular Morse theory? Well, every cellular Morse theory, this acyclic pairing on your cells in the style of Whitehead, is a selection of these atomic paths. And these atomic paths satisfy two properties. One, if you have a path x bigger than y, then x and y do not belong to any other path. If you remember our pictures with the arrows, that means that if there's an arrow from y to x, then there's no other arrow coming out of y, and there's no other arrow coming out of or into x. Right? The arrows sort of completely partition and are disjoint. And the next thing is the acyclicity condition, which is that you never have a loop coming from the zigzags, x bigger than y, bigger than blah, 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 and then back to x bigger than y. There's a sort of gradient-like structure, which is the cycles we banned in the beginning of our definition. So these are sort of axioms you've seen before. There are two more that you haven't thought about, but it's true. So if I have a picture like this on the left, I want you to think about what this means for a second. The sort of blue arrows, the ones with the circle through them, mean that path is just, so on the left is x bigger than y and nothing in the middle. So if you look at going down and then right in this picture, x bigger than y, and then there's some descending sequence to y prime. And if you go right and then down, then it's x falling somehow to x prime and then directly down to y prime. And the double arrow in the middle means that down right is a subpath of right down. So what that means is that when I went from x to x prime, somewhere in the middle, I must have contained y. That's how the partial order relationship is defined. So in pictorial terms, it just means every such square with two atoms on the side, you can find a red diagonal that sort of decomposes this picture into two pieces. And there's a similar one, the switching axiom, where if you have a completely atomic square and both sides are less than some diagonal, then you can find the other diagonal, and it satisfies this nice property that going down, up, down is less than b. Okay, so this is, it is technical, and I mean, I don't know how to dance around it, but again, if you replace everything in sight by one of these descending paths of cells, the fact that these are satisfied becomes obvious. So, for example, on the right, in the switching axiom, look at the square, the one that follows the if. X bigger than x prime bigger than y prime. That's the right down path. X bigger than y bigger than down right path. And both of them are subpaths of v, which means that there must be, x prime must be a face of y, and that's how you get that red arrow. Okay, good. So what are we doing with this? We're going to take everything that participated in the pairing of cells, this W, this collection of x bigger than y paths, and turn those around in the entrance path category. So what I mean by turn them around is you make them formally invertible. And this is sort of what it looks like. There are two descriptions of it, and I'd like you to see both. There's a sort of very combinatorial hands-on description, and then there's a sort of nice universal description. It's the same object. So the localization of this path category about W has the same objects, but now instead of just falling, using all possible sequences of faces, you're allowed to go up. This is exactly what happened when we were looking at the homology story in discrete Morse theory. So say W and Z are critical cells that are at the end. And now the zigzag means from W to Y0, you have some sequence W bigger than W1, bigger than W2, falling to Y0. So there's a whole bunch of greater thans. So there's a sequence of phases. Then from Y0 to X0, there's an atom. So now you've become Y0 less than X0. So whenever you see an arrow without a loop, just think I'm falling through a bunch of phases to a smaller phase. Whenever you see a backwards arrow with a circle, you're going up codimension 1 and then falling again, then up, then falling again. That's what the zigzag looks like. And only things in W and identities are allowed to point backwards. Those are the only things that we've inverted. That's what we have turned around. And this is sort of how you build a partial order relation between zigzags. So this is what I promised you. I told you that if you have this one, gradient flow path from a critical cell to another critical cell, and another one, you should be able to decide when one is less than the other. And this is the partial order relation. Okay, so, and again, only identities or elements of W are allowed to point downwards. So this is a standard construction called the hammock localization of a category. But again, it's very concrete, and it comes with a nice property. The property is as following. Is as follows. When you have a functor that goes from the unlocalized one, so the one without any zigzag, to the one with zigzag, so that everything in W is mapped to isomorphisms, and anything else that also maps W to isomorphisms must factor you through this. So this is a sort of Kahn extension property for localizations of categories. Again, you don't have to know what this is. It's just nice to have. And this functor is just it sends the objects to those same objects. And if you have a morphism in ent of x, which is a descending sequence of cells, remember it can be considered a zigzag that never went up. Right, so just it's a zigzag that never went zag. It just went to the right and never went to the left. So that includes naturally into the space of all zigzags. So that's the functor. All right, good. So now we are ready to define the discrete version of the Cohen-Jones-Siegel flow category. So X is a regular CW complex. You can think simplistically, you will lose no information. And say that W is a collection of things that were paired by arrows in discrete Morse theory. And now the flow category is the full subcategory of the localization, where you only consider the critical cells as objects. So again, the objects are just the critical cells. So no cell that was at the source or target of an arrow counts. Those are all thrown away. The morphisms are posets of zigzags that look let me describe them over here. So so for this picture over here that we looked at, there are going to be only two objects. Those are the two critical cells. There's an edge on top and a vertex below. Everything else participates in an arrow, so it's gone. It's not one of our objects. There's two objects, and now there's one zigzag on the left, there's one zigzag on the right, and there's no sort of relationship between them. So if you went to the flow category, it would have two objects and two morphisms that gives you a circle, which is the correct homotopy type of this space. And here's the theorem that this is true in general, that this flow category is homotopy equivalent to the original thing you started with, just like in Cohen-Jones and Siegel's result. So this is, in some sense, the discretization of Cohen-Jones and Siegel. And the proof for this is that the localization functor has contractible fibers. So we use Quillen's theorem A, and so does the inclusion functor. So, everything is a homotopy equivalence, and you just use Quillen's theorem to give it to you. Let me quickly describe why these two things are true. And I realize that time is an issue and so on, so I'll be quick about this. So we want to show that the localization functor has contractible fibers. So take an object Z, and now the fiber over Z looks like all zigzags that end in Z. So that's a typical example. assign to each one of these the sequence of descending x naught bigger than y naught, so on, going all the way down to z. Now this is, if you looked at the picture before, it's just a sequence of arrows that one comes before the other. That's all this means. And those two axioms, this lifting and switching, just makes this a well-defined assignment. And now this assignment gives you a functor from the fiber to a poset which has a minimal element. And because it has a minimal element, this poset is contractible. And so you show that this map nz that takes this zigzag to this poset of things living on top of z is a homotopy equivalence. So you use Quillen's theorem to get that this is a homotopy equivalence, and so you get that the fiber is contractible. Then you use Quillen's theorem again because you have a functor with contractible fibers. So there's two iterations of Quillen's theorem here. So that's why there are two hammers that flew into the slide here. And the fact that inclusion fibers are contractible really is sort of more intricate, and I will not talk about it. But it's true. It's true, I promise. Okay. So more generally, we didn't really need a cell complex. You can do this in a very general way, and I'll tell you why. For just any two category, if it's if every sort of non-empty space of morphisms has an initial atomic element, so the minimal element that does not factor into anything else, and a collection of its one morphisms that satisfies those four axioms, including the lifting and switching axiom, is called a Morse system. And then this localization functor, it's the same proof as I just gave you for cell complexes, induces a homotopy equivalence. And if certain sort of more technical cellular-like conditions are satisfied, then so does the inclusion of the unpaired things. So what I want to say is that these two homotopy equivalences that relate the original space to the Morse space are more general than just for cell complexes. And the reason I do that is that this general Morse theory is actually useful. So in Whitehead's simple homotopy equivalence, those arrows, you always had to go codimension 1, right? If you were an n cell, the arrow had to go to an n+1 cell. This restriction is completely removed in this new picture. You can go up several codimensions, and that's still fine. So you can go from a 0 cell to a 5-dimensional simplex. That's okay. This general theory takes care of that. And if you have any sort of homology theory or any sort of functor into an abelian category, so this could be homology, it could be something else, a coefficient system, so that the things that you have paired are sent to isomorphisms. So if x bigger than y was on two ends of an arrow, then I want f to send that to an isomorphism in A, whatever A is, it doesn't matter. Then, by the universal property of localization, you get this induced map from the localized entrance path category. And because the flow category is just a subcategory, you get a Morse version of those coefficient systems. So any sort of exotic cohomology theory, if you wanted to compute K theory or something like this, as long as the pairings of cells were isomorphisms, were sent to isomorphisms by your coefficient system, you would get an induced Morse thing, and which would be easier to compute because it's a smaller category. And here's a second question, which appeared on Math Overflow some years ago. If you're familiar with this website, it's where people ask questions about mathematics, which is, why do wedges of spheres appear so often in combinatorics? And the answer was that it's because whenever something has an exotic homotopy type, we don't have the tools to detect it. And sort of this is the beginnings of such tools. You can now actually see homotopy types that are different from wedges of spheres. So I'm optimistic that something good will come out of it. Okay, I have done a lot of tedious, dry, categorical nonsense, and I want to sort of end on a note that is not depressing. So let me give you a very concrete example, and I hope this will sort of convey the flavor now. And here's the simple example. It's a two-sphere. I hope you can see it. It's built out of 6 cells. There are 2 vertices, W and Y, at the end. And there's a front edge Z and a back face X, and then there's a top and bottom cap called T and B appropriately. So these are 6 cells that regularly CW decompose a two-sphere. So it's hollow on the inside. There's no 3 cells. And here is your pairing. So Y pairs with X and Z pairs with B. So these are sort of Whitehead style pairings. And so now you know that the things that are unpaired are only the top T that has no arrow coming in or going out, and the vertex W. And so everything depends on finding all the zigzags between T and W and what the poset structure between them is. Whatever that poset structure is, you suspend it the way we did for the Cohen-Jones-Siegel result, and you'll get, we want to get the homotopy type of S2 back. So here it is. Here's the whole poset. This is what it looks like. Now it's going to take a second, but look at the top row. The top row has T bigger than W, and on the left and right, TZW and TXW. This is just what you would get as the space of paths from T to W if you had not localized anything. This is just the morphisms in the entrance path category, right? So W is a face of T, and then W is a face of T through Z and also through X. So these are just descending sequence of cells. There's no less than yet. So that's the top line. On the right is what happens because you turned around the fact that X was bigger than Y. So in the middle, you fall from T to Y. Usually you would be done, but now you have an arrow which gives you a way out. So you can go from Y to X and then fall from X to Z. And below that, you can go to Y, T to Z to Y, and then chase this arrow up to X and down to W. So what is happening at the upper right corner is that you should have T bigger than Y, smaller than X, bigger than Y, bigger than W. So T, X, Y, X, W. And when you have X down to Y, Y bigger than X, that's, you have a morphism and then you have its inverse, because Y is less than X, it's just the inverse of X bigger than Y. So that cancels and it gives you TXW. So there's a cancellation that happens at the upper right corner. The left side of this is a similar thing that happens because you can now fall, when you fall to Z from T, you can go up to B because of the arrow, the Morse arrow. So that gives you another line with a cancellation at the upper left corner. And the bottom row happens because you can go from T to Z to B to Y to X to W. That's another zigzag flow path from T to W that you did not have before. It's only because of these arrows that you can do it. So now you get this poset, and you can see it's topologically a circle. And then you put a T on top and a W below and suspend it, and you will get the homotopy type of the two-sphere back. That's the Morse complex for this discrete Morse theory, which has the correct homotopy type. Okay, so I hope, again, I maybe this was a bit fast, but this is really how you build it. It's very concrete and combinatorial. You don't, I mean, a computer can do everything I just told you. So let me end on a sort of strange note. So you saw just now that when you had a two-sphere, you ended with this sort of circle in the middle that was triangulated like this. You know, the zigzags up and down. So what happens if you took, instead of a two-sphere, you took a three-sphere? And again, it's got two vertices, two edges, up cap, bottom cap, and then a three-dimensional upper piece and a three-dimensional lower piece. Well, you could put the same sort of matching on it, and then you would want a two-sphere to show up where the circle had appeared. And when you do that, it looks like this. So this is the sort of triangulated two-sphere you get. So there's a British flag on every face, and then the faces are glued together, if that makes any sense, right? There's the plus and then the X. That's a triangulation the two-sphere that you get if you did the same story but with a three-sphere as the beginning object. And here's a cute theorem. If you have this maximal, if you repeat this for an n-sphere, you get what is called the wild chamber decomposition for the BN root system. And if you've ever taken a course in Lie algebras, this means something to you. If you haven't taken a course in Lie algebras, you should, and then this will mean something to you. But it's the action of the BN root system, and this is the fundamental domain of it, Rn. Okay, that is honestly the end of my talk. And before I open this for questions, I want to sort of acknowledge what got me here. This picture is from, I think, 6 years ago. There was a seminar that happened starting at 8 o'clock at the Institute for Advanced Study and going up till maybe midnight every Thursday. And it was run by Bob McPherson, who's in the middle, the tall guy, and then Mark Goreski, who's right in front of him. And some of the people here are Justin Curry, Amit Patel. So we just got together and talked. And none of this work would have happened. Here are the two papers that relate to it. One has appeared earlier in the Journal of Pure and Applied Algebra, and the new one is about to appear in Advances with the collaborators Dai Tamaki and Kohei Tanaka. Okay, with that, I would like to end. Thank you for your patience, and I'm happy to take your questions.
Many thanks, Vidit. Are there any questions?
I have a question, or I have two questions actually. Can you hear me?
Yeah. Yes, I can.
Okay, so the questions are going in two completely different directions. The first question would be, now you can figure out the homotopy type, and in the beginning you showed us all those examples. So do you have any idea where this additional knowledge would be helpful? And the other question would be, now that you know the homotopy type, is there any idea whether you can figure out maybe even finer invariance from point clouds that you measure on some set? Like, for example, assume you know that it is on a manifold, the point cloud, that you figure out some diffeomorphism invariance or something like this?
Oh, right. Well, unfortunately, knowing the homotopy type is not helping me at all with diffeomorphisms because, a circle and an annulus have the same homotopy type and they don't have the same dimension or anything like this. So,
yeah, now we are listening to you again.
Okay, great. Anyway, I was saying that this was not to avoid your question, Franz. This was a technical thing. What I was saying was we don't have the homotopy groups of the space necessarily. We do have a new space that has the same homotopy type. All I proved was the original thing is homotopy equivalent to the new thing. But of course, there are all sorts of issues with putting not as the Morse complex up to homotopy has been correctly built. Going from this to diffeomorphism invariance is, I think, a hard and sort of very open problem. This just happened. I don't have a good idea for how